Hey there, and welcome to The Explainer. Okay, so we've all seen those perfect repeating sine and cosine waves in math class, right? But what happens when a wave doesn't start neatly at zero? I mean, how do you even describe that mathematically? Well, that is exactly what we're going to figure out today. So here's the game plan. We're going to start with the big idea. What even is a phase shift? Then we'll decode the formula that actually makes it happen. After that, we'll see how to graph it, which is super useful. And then, the fun part, we'll model some really cool real-world stuff and use our model to pinpoint a specific moment in time. All right, so first things first, what's the problem we're trying to solve here? Well, a perfect sine or cosine wave, it just goes on forever in both directions. But think about it, real-world things, like when a Ferris wheel ride starts, have a very specific beginning. And that creates a little bit of a mismatch we need to fix. So yeah, how do we do that? How do we take that classic wave that we know and love and just slide it over on the graph? The answer, you'll see, is actually pretty straightforward. And it's the key to this whole thing.
And the answer is called a phase shift. That's the official term. All it means is we're shifting the function horizontally, left or right. It's the tool that lets us grab the entire wave and move it to the exact starting point we need it to be at.
So how do we actually control this shift with math? With an equation? It might look a little intimidating at first, but it really all comes down to changing just one single number inside that standard formula for a wave. Okay, here's the whole shebang. You've got A for the amplitude, which is how tall the wave is. D handles the vertical shift, moving it up and down. B messes with the period, stretching or squishing the wave. But our hero today is C. That little variable right there is what gives us the power to control the horizontal phase shift. Now listen up, because here is the one thing that trips everybody up when they're first learning this. As one of our sources perfectly puts it, the direction of the shift is totally counterintuitive. It's the number one mistake people make, so let's make sure we get this crystal clear. So here's the deal, and you gotta burn this into your brain. When you see x minus c inside those parentheses, the graph actually shifts to the right. And when you see x plus c, it shifts to the left. It feels backward, I know. The reason is that for the wave to start, the stuff in the parentheses, like x minus c, has to equal 0. Well, for x minus c to be 0, what does x have to be? A positive c, and that's what creates the shift to the right. Okay, theory time's over. Let's move from the formula on the page to an actual graph on the screen. How do we take this weird, backward-seeming rule and use it to actually draw a wave that's been shifted over? It's really just a simple three-step trick. First, just imagine one cycle of the basic wave, from its start to its end. Second, you take those start and end points and just add or subtract c to slide them over. And finally, once you have that new window, you just sketch in your 5 key points, the top, the bottom, and the 3 middle points. It's as easy as that. Now this is where it gets really, really cool. This abstract math stuff isn't just for tests and textbooks. No way. It's an unbelievably powerful tool for describing all sorts of real-world cycles, from things people build to patterns in nature. Let's kick things off with a classic, a Ferris wheel. But notice the key detail here. The ride doesn't start at time 0. William gets on at the 5-minute mark, and he starts at the lowest point. This is like a textbook case for needing a phase shift. And you can literally see the wave pattern right here in the numbers. See that? William starts low at 2 feet, he goes all the way up to a peak of 82 feet, and then comes right back down. Our mission is to capture this exact journey with one equation. So before we build the whole equation, let's just find one key piece of the puzzle. The problem tells us that one full revolution takes an hour. Well, that means the period of our function, the length of one full wave, is 60 minutes. And you can see it in the data too, right? He gets back to the bottom at 65 minutes, which is exactly 60 minutes after he started at minute 5. And voila! Here is the final model. We use a negative cosine function because he starts at the bottom of the wheel. The amplitude is 40, which is just half the diameter. That number 6 inside is tied to the 60-minute period. And look, right there, inside the parentheses, x minus 5. That's our phase shift. It moves the whole wave 5 minutes to the right to perfectly match when William's ride actually began. Okay, so let's level up. Let's see how these exact same ideas can be applied to a much bigger, more natural cycle. Can we use a phase shift to model the ebb and flow of the ocean tides?
Of course we can. So here's our data from a tide report in Salem. We've got a high tide at 10:15 a.m., that's 615 minutes past midnight, then a low tide, and then another high tide. Once again, it's a super clear, predictable cycle that doesn't start neatly at midnight, aka time zero. Let's find another one of our key parameters. The tide goes from a high of 9 feet down to a low of 1 foot. That's a total change of 8 feet, right? Well, the amplitude is always just half of that total range, so that gives us an amplitude of 4 feet.
And here is our beautiful model for the tide. We're using a positive cosine this time because our data starts at a high point. That weird-looking pi over 360 term, that comes directly from the tide's 12-hour cycle. And would you look at that phase shift, x minus 615. This slides the peak of our cosine wave perfectly to the right, lining it up exactly with that first high tide at 10:15 a.m. It's awesome.
So why do all this work? I mean, what's the point? What's the big payoff? Well, the real power of building these models is that you can use them to make predictions and answer really specific questions. So let's use our brand new tide model to answer a practical question. Let's say you need the water to be at least 8 feet high so you can launch your boat. We know the peak is 9 feet, but at what times exactly will the water be 8 feet high? So how do we figure that out? Well, we're basically just asking, for what value of x, for what time, does our function equal 8? If you think about it graphically, all we're doing is finding the exact points where our wavy tide curve crosses the straight horizontal line y equals 8. And here are the answers. Because the wave goes up and then comes down, it actually hits that 8-foot mark 4 different times during the day. This just shows you the incredible predictive power you get when you build a model with the right phase shift. And look, this tool isn't just for Ferris wheels or tides, it's used everywhere to model daily temperature changes, sound waves, the alternating current in your walls, so much more. So, the next time you see a repeating pattern out in the world, ask yourself, I wonder if a phase-shifted wave could describe what I'm seeing. Thanks so much for watching.